Hello, my name is Ale Alakar. I will be your presenter today, and today I am going through a research article called A Deep Reinforcement Learning Approach for Adapted Traffic Routing and Next-Gen Networks. The original authors are Akshita Abrol, Purnima Murali Mohan, and Tram Truong Hu. Traffic routing is a crucial aspect of maintaining an efficient network. Traditional routing techniques make it difficult to handle with network growth and demands, especially since traditional routing was used to smaller network compared to what the network growth we have right now. However, adaptive traffic routing using AI has been explored and researched recently. Deep reinforcement learning has demonstrated substantial advancements in decision making and automated control. However, computer networks are typically represented in graphs, but graph neural networks help with organizing this type of data in graph structures. There have been many researches using AI for network optimization. For example, there have been research done to dynamically learn and update the network state using radio access network. Furthermore, there has been research done to address the routing problem in optical circuit switching networks through the use of message passing neural networks. However, this research article will be using deep graph convolution neural networks to help optimize adaptive traffic routing. To train this model, they'll be using Markov decision process. Now, a Markov decision process uses state, action, reward, and probability to deal with decision making. State space helps with capturing the best topology of the network using link and node state. The link state represents the up-to-date topology of the network and is represented in the form of a network adjacency matrix. The network adjacency matrix has the weights Wi and Wj, which I is the source node and j is the target node. The network state is defined by S-link equals d to the negative 1/2 power times w prime times d to the negative 1/2 power. Now, d is the diagonal node of w prime, and w prime is the sum of w plus I, or the identity matrix, and w is the weights wi and j. Node state is represented by a feature vector which consists of node degree, node importance, aggregated egress rate, aggregated ingress rate, source nodes, destination nodes, and requested data rate. Action state represents the probability of choosing a path for a traffic request, and the reward symbolizes the overall utility of sending the data through that particular path. The reward function is defined as the actual throughput divided by the requested transmission flow rate plus 1 over the delay. Probability is defined as P S prime and S and X, S and AF. S prime is the target state, while S is the individual state that the algorithm is right now, and AF is the action state based on flow request. However, it is quite difficult to derive a closed form formula to compute the probability, since there is a lot of space and topology. The Graph convolution neural network has three stages: the graph uh, convolution pooling, and traditional convolution layers, followed by a dense layers of path prediction. Graph convolution stage computes node latent representations by propagating information between neighboring nodes. Pooling stage combines node representations with into a vector with a predefined order and size. And the graph is represented by a latent vector and is given as an input for further learning of local patterns to one-dimensional convolution layers, max pooling layers, even a fully connected layer, and a softmax layer for predicting Q values. Now, from the top left, we have the network topology, and as it goes through, we have the layers, which use the RELU activation, which is the rectified linear unit. RELU is defined by rectified linear unit, and RELU outputs positive, and if it's not positive, it will just output 0. The activation is used to obtain node representations that capture info from the entire graph. And after the pooling, we have the sort pooling, which is used to arrange nodes based on the sum of the features at the final layer. If a tie were to ever happen in the pooling, then the algorithm will resolve it by looking through the previous layers. And through this pooling, we get the Q values, and we use those Q values for exploration and exploitation. And through that, we will go map the action for routes and do a sort of action, and you look through and look at the network environment based on like next state, congestion flag, delay, throughput, and reward, and we will store those in the replay buffer and use those for the next time, the next iteration of looking through the network environment and rewards. So at time on the right side, we have like the pseudocode for the formula. At time instant t, the deep reinforcement learning receives a traffic flow request that is defined by the tuple source and destination, and the requested traffic flow. The DRL agent uses the main model to calculate the path for traffic flow. And AFT is the traffic flow action, which makes the network transit to state and incurs a reward, ST1, and incurs a reward. AFT is calculated using the exploration and exploitation trade-off, which is this on the near the where it says greedy policy. For the greedy policy, epsilon equals 1, and if it's less than and the threshold is randomly generated number distributed between 0 and 1. Epsilon decays exponentially every episode with the rate of 0.99995, and the minimum value of epsilon is set to 0.01. The threshold value is calculated through the mean of the last 100 rewards during exploitation state. And the reward value kind of fluctuates, and if that reward value fluctuates outside of threshold value, epsilon is set to 1 to enable the model to explore and adapt. Furthermore, it uses a congestion flag, which indicates if the allocated path exceeds maximum link capacity. Experience buffer stores 1,000 samples to help train the model, and priority of flow is calculated using the temporal difference error, which is seen on the right side. And the Q value of the target model is calculated by the Bellman-Ford equation on bottom. And also the model starts learning once the length of the replay buffer is more than batch size, and batch size is denoted by minimizing the loss function using stochastic gradient descent. Here, so the setting of the testing of the deep reinforcement learning algorithm. The deep reinforcement learning algorithm was implemented using OpenAI GEM framework with TensorFlow and Stellargraph. Network topology was modeled using the Network X library. Performance was evaluated using two topologies or two networks, one being a random 9-node topology with 6 lanes and NSFNet. And NSFNet is a network that has 14 nodes. Each node was connected to a single host, and end-to-end throughput and end-to-end delay are the performance metrics for testing the algorithm. Delay is calculated by summing the transition and propagation delay, and baselines, which is to help compare the algorithm. We have the DRL framework with MLP for neural networks and OSPF routing algorithms. So analysis of the experimental results. We can see the researcher's algorithm is able to achieve the best results by maxing the reward, leading to increased throughput and decreased network delay. It also stabilizes after 500 episodes, and the deep reinforcement learning MLP failed to solve route optimization after 2,000 episodes due to lack of topology and large action space. And you can see the evidence of the research. For example, in figure 2 on the top right, you can see based on random network and NSFNet, generally the research team's framework was a bit better. There have been some spikes where the MLP was around the same performance of the GCNN, but for the most part, it was mostly GCNN was outperforming it. Also, in the figure 3 on the bottom left, you can see that even in random network NSFNet, GCNN was outperforming with a few outliers. We can see the delay incurred through both both algorithms on the random network and subnet, and you can see that for the most part, the MLP was having a lot more delay compared to GCNN. So there were two other scenarios that the research team did was decrease the traffic demand and increase the traffic congestion. That GCNN adapted well with traffic fluctuations and new traffic behavior. Approximately 500 epochs were required for adaptation to traffic patterns. The decrease in traffic demand and increase traffic congestion had expected results, where in decreased traffic demand, there was a lot less congestion, and for increased traffic congestion, there's a lot. It was congested, but based on reward, it's from figure 5, the reward obtained through various traffic, the traffic variations. We can see by decreasing the traffic demand, we can see a higher reward compared to when we increase traffic congestion. There was a spike in a decreased spike in reward, but not too bad. In GCNN, there was another test where the research team froze the GCNN after 2,000 episodes and tested against traffic variations without the algorithm being able to update, and the traffic rate in that test was increased after every 10 episodes, and with GCNN, it increased network throughput by 5.1 and 7.8 compared to OSPF, and by 39.4% and 69.2% in base compared to the MLP. And GCNN reduced network delay by 16.1% and 17.5% compared to OSPF, and 66.5% and 71.2% compared to MLP. We can see on the left there was the performance based on throughput and delay for the random network. We can see the blue line is for MLP, which had really bad throughput compared to the OSPF and GCNN, and high delay compared to both other frameworks. OSPF had similar performances compared to GCNN, but as it increased the traffic demand, it started to slowly decrease. But it was not far off. But it did. GCNN did increase throughput. You can see also that GCNN and OSPF had similar performances in delay, but OSPF slightly increased as demand increased. And you can see on the right we have the MLP we can see the performance of NSFNet based on the increasing traffic. We can see the throughput and delay, and we see that MLP was outperform. Was not performing as good as the other two in throughput and delay, and you can see that again GCNN and OSPF were around the same performance. However, in delay, we see that the gap between OSPF and GCNN was smaller. So, in conclusion, the research paper presented and developed a deep reinforcement learning framework using deep graph convolution neural networks for adaptive traffic routing. They proposed traffic features at link and node states to form a graph-based data structure to train the GCNN framework. And they also developed a training model that uses exploration and exploitation to train the model. And they also tested the GCNN framework on various scenarios and compared them to OSPF and MLP. For future work, they would intend to integrate the SDN controller and investigate the impact of other DRL techniques. Thank you.